Hi guys, so today we are going to be doing Module 4, Chapter 11, Transformations, Symmetries, and Tilings. So let's get started with question 1. So for question 1, Ephraim and Devante were asked to reflect the pattern block figure shown on the left over the horizontal line through the center of the square. They rearranged the blocks to form the figure on the right. What type of rigid motion did they use? So if you look at the figure, they used a straight downwards translation of the top block and reflection of the bottom block. So how would you help clear up their misunderstanding? So as you see, they did reflect the bottom block over correctly. However, they did not reflect the triangles correctly. They are reflected wrong, or they did not reflect them. So how would we clear up their misunderstanding? So here is our figure that was shown on the left. And this is what the triangles should look like when they're reflected over the horizontal line. So let's go to question 2. So for question 2, we are given these figures, and we have to figure out which figures have one line of symmetry. So this figure right here does not have any lines of symmetry. The diamond has one line of symmetry. The triangle has one line of symmetry. The half circle has one line of symmetry. The rectangle has one line of symmetry. This triangle has one line of symmetry. And this hexagon has one line of symmetry. For part B, we have to figure out which shapes have rotational symmetry but no reflection symmetry. So this shape has rotational symmetry because it can be rotated 180 degrees and look like this exact same shape. This shape can also be rotated 180 degrees and look like this exact same shape. Now for C, we have to figure out which shapes have reflection symmetry and rotational symmetry. So the rectangle has reflection and rotational symmetry because it has one line of symmetry and it can be reflected and folded over, and it can also be rotated 180 degrees and look like the same shape. The same goes for the diamond and for our hexagon. Now let's go to question 3. Myra cut out a regular pentagon, hexagon, and an octagon, and it seems to her that they form a vertex figure such as the one shown below. Is Maya correct? Let's figure it out and create the figure. So we have our octagon, our hexagon, and our pentagon. Our pentagon interior angles are 180 degrees. Our hexagon's angles are 120, and our octagon's interior angles are 135. So we have to know that the measure of the interior angles meeting at a vertex figure must add up to 360. So we need to add our interior angles together. So we would do 108 plus 135 plus 120, which equals 363 and not 360. So Maya is not correct. But how could we change this into a vertex figure? So to turn this into a vertex figure, we would have to put this 3-degree gap right here in between our figures. Now let's go to question 4. So for question 4, part A, we have to demonstrate why triangle QPT and triangle SPT are congruent and why it is true. So let's look at these two triangles. So as you see, QPT and SPT are congruent, and they are congruent because if we folded over triangle QPT onto SPT, they would fit exactly. and they're exactly the same. They fit right on top of each other. So that is why they are congruent. So now let's look at triangles QPV and SPV. So these two triangles are congruent because you can flip them or fold them over vertically and they fit the same right on top of each other, which means that they are congruent. And the reason why angle QVP is a right angle is because it fits exactly right here. And yeah, let's go to question 5. So for question 5, a regular pentagon, penta, and an equilateral triangle, PQR, are both inscribed in the same circle centered at O, with P a common vertex. We have to demonstrate our calculation of angles NOQ. So let's get started building our figure. So here we have the circle, and we have our pentagon. Let's name it penta. And then we add our triangle and share their common vertex and the circle centered at O. So we have to figure out this little angle right here in OQ. So let's get started. So as you see, these angles form a triangle, OQP, and we can put this over here to the side, and we know that a triangle's interior angles add up to 180 degrees. So we can figure out that the acute angles are both 30 degrees, and the obtuse angle is 120 degrees, and this adds up to 180, and we will use this later. And then we have to figure out the interior angles of our pentagon. So to do that, we would do 5x equals 360, and we would divide 360 by 5, which is 72. So the angles, our interior angles, are 72 degrees. So this means that angle QO is 72 degrees, and angle OP is 72 degrees. And when we add 72 and 72 together, that equals 144. So now let's go back to our triangle right here, and we use our obtuse angle, 120, and we subtract that from our angle right here, 144, and it equals 24 degrees. So our angle NOQ is equal to 24 degrees. Now let's go to question 6. So for question 6, by holding a ruler 2 feet in front of her eyes as illustrated in the diagram, Jenny sees that the top and bottom points of vertical cliff face line up with marks separated by 1.5 on the ruler. Jenny is about a quarter mile from the cliff. What is the approximate height of the cliff? And recall that a mile is 5,280 feet. So to begin doing this problem, we are going to discuss the similarities of triangles in this problem. So we have two triangles. We have this little one right in front of her, and I made it a little bit bigger. And then we have this one right here. So let's name these triangles. So we have A, B, C, triangle ABC, and triangle D, E, F. So as you can see, angle D is congruent to angle A, E is congruent to B, and C is congruent to F. So, for example, if we shrunk this triangle down, it would be the same exact triangle as triangle DEF, even though the ABC is bigger. Anyways, so let's get started to figure out the height of our cliff. So we recall that 1 mile equals 5,280 feet, but Jenny is standing a fourth or a quarter of a mile from the cliff. So we would divide 5,280 by 4, which equals 1,320 feet. We also recall that 1.5 on a ruler is equal to 0.125 feet, or 1.5 inches. So let's get started. So we would divide, we would divide 2 over 1,320, which equals 0.125 over the cliff. And the cliff equals, in parentheses, 0.125, in parentheses, 1,320 over 2. So we would times these two together and put that over 2, which comes out to be 2 over 1,320 equals 0.125 over 82.5. So that means that the height of the cliff is 82.5 feet. Thank you, guys.